Hello, this is Jonathan Hinkle. I'm a distinguished researcher at Lenovo and lead our system architecture research. Today, I'm going to talk to you about the persistent memory connection, how to attach persistent memory in computer systems. Just some basic agenda here. We have some background basics that I'll take you through about the memory problems that we're having in systems today, persistent memory and how that can be part of the solution. But then the question is, how do we attach that? So the first step, I'll take you through some existing interfaces and slots that we can use for attaching persistent memory today. And then step two, we'll look at more, how do you optimize persistent memory in computers and really solve the next generation system problems? Also, we've been leading some system architecture research at Lenovo on this type of new types of optimization for persistent memory, and I'll take you through some of our early preliminary results on that. So for the computing basic system architecture, really we've been using memory attached over DDR as the main interface for a long time. This is just an outline of our basic architecture for a computer: storage, memory attached to a processor, directly to a memory controller in the processor, and I/O. And this is the same really basic architecture we've had for a long, long time. And if you're familiar, DDR is the electrical interface that we've had for DRAM directly attaching to the memory controller, and we use memory modules called DIMMs. And really the key memory needs for data center, we really need this high capacity and we need high performance. Lots and lots of data to be stored in memory while the processor is working on it, and high performance for access to that data. Now, the problem is with DRAM, we've really started hitting some scaling issues where it's harder and harder to make the next generation of DRAM and make it faster and higher capacity. As you can see over here on the left, we have memory interface speeds that have started slowing down as far as how much improvement each generation has seen. And then also the capacity is not growing as much as we'd really like it to. At the same time, the actual implementation of the systems also has become more and more difficult with the number of DIMMs per channel, the number of actual cards we can plug in. It's harder and harder to plug in more of those while running it at faster speeds. This is all compounded by the annual data growth. So we keep having more and more data generated, more and more sources of data over in the world today, and that's driving this increasing demand for memory capacity. So while memory and DRAM, the traditional ways we've been leveraging it in systems, is slowing down, we're having an increased demand. And so we have new technologies like DDR5 that are coming out from JEDEC, and these are excellent new technologies that will fix some of the issues as we've seen in the past, but they're still evolutionary. They don't fix this fundamental problem of speed versus capacity. So also in data center systems, this is a server, a two-processor server. We're hitting significant challenges with the physical space that we have to plug in the DIMMs. So you can see the DIMM slots that are plugged in directly next to the processor. And this one has 12 DIMM slots, so 6 per processor. If you go to, or 6 per side here, if you have basically more than that, 16, then that fills up the entire space end to end in this server. And how do we expand past that space? It's going to be harder and harder. And one of the things we've done just to be able to fit this number of DIMM sockets for the number of memory modules is we've actually spaced them closer and closer together. Well, these are air-cooled systems, so mostly. And so as the air goes down between the DIMMs, it's harder and harder to get the air to flow, and it's harder to get the heat out of the memory modules. And so plugging more and more DIMM sockets in there, more and more DIMMs, then it's harder and harder to cool. So the problem is really we need to keep expanding the memory capacity, improving the performance of memory just to keep up with the amount of data that's being now generated. And if we don't, then we can't really unlock the value of that data. So we've really got to continue to improve the performance and the capacity of memory while not breaking and power pooling in the space it takes up. So persistent memory, thankfully, can be part of that solution. Basically, it helps to promise to fill some of the gaps. So you can see, basically, in our memory hierarchy, we have sort of the latency of what that memory is versus the capacity overall, how much data it can store. And persistent memories have new advantages. They're usually higher capacity, and they can also be lower cost per capacity, which really fills in some of that gap as we keep wanting to expand that capacity of memory while still maintaining performance at a low latency. Also, persistent memory also has this advantage of non-volatility, which can provide a new disruptive benefit. enabling some different significant speed ups where workloads can take advantage of the fact it doesn't have to write to a slower storage. Still, the problem is persistent memory doesn't really follow the same rules as DRAM. It has different endurance where it can wear out at different time than DRAM, where DRAM is right now unlimited endurance. The error rate is maybe higher, and there's some management that has to be done for a lot of persistent memories. The power may be higher, the size can be different, the timings to access electrically to the chip can be different. So all this is different from DRAM, and that really drives the point, how do we plug them into systems? Because this is, the systems today are just not designed for this. So step one is we can really look at the existing interfaces and slots in the system and think about where and how can we attach persistent memory. So one way is we have NVMe drives, a PCIe attached SSD. And that's definitely one of the easiest ways to plug in persistent memory. We can plug it in and just use it as a very fast storage device, has a known slot, power envelope, and an easy software stack that's the exact same as with flash drives today. We can leverage that for persistent memory. So it aligns very well for all the ways that a customer could adopt it quickly. And we can design it into systems. But the problem is, unfortunately, persistent memory is really pretty expensive per gigabyte versus flash memory, which is what's used in SSDs for storage today. And so it will take a long time before it can really be used for all the main storage, like flash right now, can be used in systems. It's sort of similar to how we had all flash versus hard drive. All flash was just way too expensive at first because for the capacity that we needed in a system. Also, the block I/O device, so it's really an interface that is intended for this slower device, and the software stack itself to access that are much slower than what we'd like for persistent memory. It actually can constrain the performance significantly. So we're not really unleashing all that performance that comes with the persistent memory inherently. So we'd like this use, this ease of use and scaling, but we really want the performance that you can get with persistent memory. So we want that performance. Another way we could attach is as a DIMM. And one of the first persistent memory modules that we've seen, has been around for a while now, is called NVDIMM-N. And with NVDIMM, it's actually a DRAM interface to the system. It's just like a DRAM DIMM, except that when the power goes away, then it copies the data to the flash that's on the same module. And then when the power comes back up, then it can restore that data back to the DRAM, and you can run like it was always there. So benefit here is it doesn't slow the system down. It's the same speed. You can plug it into the same memory controller. So again, the same slots and existing interface that we have. Unfortunately, though, then it does have to play by the DDR rules when you plug into that slot. It's very useful for small capacity like storage metadata, could be data journaling, database journaling, or recovery logs. Smaller amounts of data that they're written very frequently, but you cannot lose that data. Unfortunately, it's very good for that, but it's still pretty expensive because you have to put it on the DRAM like you would a normal DIMM, and then you also have to put the flash, which is some cost, and then the logic, the controller, power, a subsystem, and an energy source to hold it up while the data is being copied if you lose power in your system. So all together, it's a more expensive proposition. So you really only use it where you absolutely need it, which is in some of those cases before. You get a high performance speed up. Also, the capacity is pretty low, again, to the terabytes typically of storage that you have in a system today. So it's not as useful for caching. It's useful for small amounts of data to be written quickly, but it's not really a good ratio for storage to a cache like we do with SSD to hard disk drives. Also, you can't access the flash, the non-volatile memory, during runtime. So really, we're just using DRAM during runtime, and we're paying for the flash, but we can't really make use of it. So that's sort of a wasted resource, not being able to access that memory. So really, we want this performance closest we can get to DRAM, but unfortunately, we still want that capacity, and we also want it at lower cost. So just a recap, where are we at with existing system interfaces and device slots? So we have PCIe and NVMe drives, which are really designed for memory, flash memory and storage, which gives us that scalability, the flexibility, but it's high added latency, so it limits your performance. Also, you could put it into a DDR4 DIMM socket just the way it is today, that's made for DRAM and main memory, which gives you that really low latency interface and high performance, but it's limited on capacity, and the scalability is just not really there. We're already having problems with DRAM scaling as far as the capacity already. So we've actually completed this. This is done. We've plugged into existing system slots. Persistent memory is already there. But unfortunately, it leaves a lot of the persistent memory value on the floor. So there's a lot more of the value of persistent memory to be unlocked. So that's where we can go to our next step. How can we optimize persistent memory in computing systems? So we've done the first step, and now the industry has had an opportunity to go through that learning experience and see those first opportunities for a strong value add. Now we've had time to understand and roll those learnings into a new design. So one of the ways that we're going to be able to do that now is NVDIMM-P. And also there's Intel product, this Optane PM+CS that's been launched already that provides a similar kind of benefit. NVDIMM-P is a persistent memory module and as well as a system interface that's really optimized for attaching emerging persistent memory in the DIMM socket, and also to run alongside a DDR attached DRAM DIMM. So this is something where you actually can access the persistent memory more directly, but still get that low latency. The other benefit, obviously, is then we can unlock the capacity. So unlike that NVDIMM-N, where we had to flash only for the non-volatility, now we can actually leverage the persistent memory capacity and really get the benefit overall of a larger memory subsystem. So NVDIMM-P, here's some general benefits. I mean, we really have the persistence. So if you don't have to write to storage, then you can keep the data in memory and get that performance speed up. Also, we abstract the memory media. So instead of having a certain type that has to be designed in, a certain memory controller designed in with a certain memory type, then now we can support pretty much any memory media with the NVDIMM-P protocol. Also, like we were talking about before, we can have higher memory capacity, so we can get that memory capacity that persistent memory allows for with expanded addressing that memory directly. Also, we have plug and play interoperability. So again, we can interoperably plug in a DDR, DRAM in the same bus with like an NVDIMM-P, for example, and that'll work during runtime. And so here's some other benefits. Really, these are the key features that we have to allow for in the standard that we've enabled in the standard to enable those kind of major benefits that we see for NVDIMM-P. So these are new NVDIMMs that really provide the capacity at that highest performance. And that really gets us, a certain way down the road for solving some of our needs. But still, it's space constrained. You saw those DIMMs in the system, and there's still only so much space. And so that's still a challenge. So the question is, how can we scale and get even more memory into a system? How can we even drive more capacity? Well, we have to look at new systems architecture to be able to do that. We have to look at, not just, what's a new way that we can attach with the same slots, but also how can we attach with new interfaces and existing bays. So coupling those together. So where we've had this existing system architecture with processor, memory attached, and a bus with storage on it, a local bus I/O with storage and Ethernet. Now we can go to a future systems architecture where, again, you saw NVDIMMs as attached through DDR or NVDIMM-P protocol. Also, you can see the storage that's sort of the slower storage. We can disaggregate that. So we can put it over Ethernet and have it as an external shared resource, which helps with cost and so on. But there's still some capacity scaling that I was mentioning before. And really remember, persistent memory provides that lower latency than flash, but really the higher capacity of DRAM. And that's really where we want to be able to scale it so that we can get a good ratio of the amount of persistent memory to storage. So that's where these new low latency interfaces come in. We have CCIX, C6, and CXL as two of those. And those allow for the latency that we need to attach larger capacity persistent memory. We can still attach NVMe SSDs, so flash SSDs over PCIe, but we can also leverage that same interconnect with these new protocols, these new interfaces, to scale and expand memory. So with this new low latency fabric kind of approach, these new interface technologies, we can expand memory resources in a way that's really meaningful and solve some of that problem for capacity. So C6 and CXL, they're really around the lower nanosecond range, so it doesn't impact the memory latency so much. Right now, DRAM, for example, is around 100, 150 nanoseconds on a DIMM directly to the processor, and C6 and CXL don't dramatically add to that in a way that causes it not to be usable as memory. We had that low latency. And what we saw is that we can realize really new benefits because we can use these interchangeable interconnects the same as we have for PCIe. So, a slot that we already have enabled for PCIe, that we can leverage it for a device, a memory device that's attached to like CXL. Also, the form factors for NVMe drives, such as EDSFF that we've recently standardized, are perfect as a perfect fit for enabling sort of the scaling of memory devices in a system. So we have C6, that's what we have available today for prototyping. And so our current lab work has been based on that. But a memory expansion with a system architecture, it works well with C6 or CXL. It's the same approach with the same method. So they're both low latency interfaces and work similar ways. So for our Lenovo research system architecture, I'll tell you a little bit more about that. We're looking at EDSFF, the E1 to S, the EDSFF 1U short drive, and that's being leveraged today for NVMe flash drives and to really scale out the number of devices. But we can leverage those as exact same slots, and instead of using PCIe, we can leverage C6 or CXL to attach DRAM or persistent memory. So with this system architecture, notice that we don't touch the DDR bus. And so the DDR bus can be used for only DRAM if we want to, or we can also complement with NVDIMMs to allow for the lowest latency and highest bandwidth to a smaller amount of persistent memory, but then scale the largest amount of persistent memory in a way that truly expands out with just even the physical space, as well as the power and the cooling to enable for that. Also, what we have is a paradigm that because the DDR is faster, higher bandwidth, lower latency, we can consider that more like near memory, so nearer to the processor where it's going to be, that data is going to be computed. And then the far memory is what we're calling this memory that's off on the C6 or CXL interface, so scaled out, but a little bit longer latency. So it's not going to be exactly the same latency between near and far. But the link interface of this C6 or CXL protocol really allows you to have this further distance between the processing, the compute, and the memory that you're scaling out. So that really gives you the space to expand and have more memory capacity. Also, again, the interface is in nanoseconds of latency. So the performance that you're going to get is going to be more like memory and not like storage of microseconds. Also, we can just add more and more devices to scale the capacity. And we really want to scale capacity with bandwidth because we can scale the data set, but we need to have the bandwidth to access that data set and scale that together. So we don't just sort of strand capacity that's hard to actually get use out of. So with this architecture, we can really still have hundreds of nanoseconds instead of microseconds of latency for memory accesses, but then expand to terabytes of data without really scaling up the cost. Because this can actually leverage the same hardware interconnect as what we already have today in systems for the most part. So this translates into system performance and lower costs for customers that are running memory and storage intensive applications. So I've given you an overview of how we've been using persistent memory today. We've already used it in the industry and existing slots. And then you've seen with DIMMs and now these new emerging interfaces, how we can leverage persistent memory. What we've been doing in Lenovo research is also going ahead and prototyping this to try to push forward the bleeding edge of where this technology is and understand it, really to understand where the value lies. And we actually have prototypes in our lab with partnerships, technical partnerships we've had to push this forward and understand what are the latest ways that we want to use this. So we actually have some measure results, and I'll share those with you now. So this is our Lenovo research prototype, our first prototype system. We've been partnering with AMD and Xilinx, along with many others, to look at, what are the different ways that we can leverage, again, memory attached to these new interfaces. What you have here is a Versal ACAP, which is their latest chip. It has programmable logic similar to FPGA. And in that programmable logic, that ACAP, there's actually a C6 to DDR4 controller. And that basically it bridges from C6 interface to DDR4 DRAM on the card. And this server from AMD allows for the interface, C6 interface, to attach to this card. And it basically allows for us to add memory into the system, into the memory space with this card. So just like we see a certain amount of memory from the DIMMs, we actually plug in this card and we can see more memory in the system. We boot up Linux and we see, instead of, if we had 16 gig, we can see more memory, and we see that 32 gig or so on. So we can see more memory, and it's directly usable by the workloads. And so leveraging this, we've been able to look at prominent data center workloads that really, what we think is going to benefit from this expanded memory. Some of the ones we've looked at relational database, we've looked at in-memory computing, we've looked at big data and software-defined storage. So really looking for memory-intensive, data-intensive kind of applications that would benefit. So from our first investigations, we've actually especially looked at MySQL as a database, and some initial results that we found. And this is still somewhat of a sensitivity study. What we're able to get is up to a 2x workload performance benefit. So what that means is, with a certain database of MySQL, we were able to get 2x the performance of the database, not just the device. And that was really interesting to us, especially because obviously MySQL and relational database, traditional databases are extremely common. It's a very, very large usage market for it. So, really MySQL, this performance, what we saw is there really is this benefit. It could be used as an acceleration to have this expanded memory. And we were comparing the 2x, basically we were comparing NVMe drives versus leveraging this expanded persistent memory. In this case, it's actually DRAM. But we basically saw some significant value there that really was promising for future workloads. Some other results I wanted to share with you. We partnered with a company called Formless Black. And Formless Black has a software called Forza that's really a production optimized RAM drive. It provides this block interface to workloads. So it leverages memory underneath it, but then it basically provides this like normal storage device to the workload. So really any workload can use this. And so what we compared here is, again, an NVMe drive versus this Lenovo prototype and running in the farm memory. And when we compare that, we looked at latency and a certain number of jobs. So how many different jobs we're going to run at the same time, and also across VM. So how many virtual machines that we were running. And so for the NVMe drive versus the farm memory, we actually were able to get huge improvement in latency, which is really what you expect, because we were able to leverage the performance of memory instead of the performance of flash, of DRAM instead of flash. But this proves out really a farm memory approach can allow for caching, can allow for speed up system acceleration through the speed up of basically expanded memory, leveraging it as a block device. Also, you look at bandwidth, we had huge speed ups in bandwidth as well. So really just first taking a stab at, what is the block device performance, what's the storage performance, that then turns into a workload performance with storage workloads, storage intensive workloads. So this is really another way we can leverage farm memory. One of the other benefits of farm memory is then, we didn't take up any memory in our main memory subsystem. So we didn't use any of the memory in our DIMMs in the system to do this. So we actually were able to speed up the system without touching the regular, what we call near memory. We're only using the farm memory for this. So it's a way of accelerating the system without stealing away any resources from in the system from your overall workload. So just a summary, so we've attached persistent memory in the existing slots and systems, and really that first wave of adoption is complete, and the industry understands the value there in existing slots. But now the industry has had time and has completed the definition of the standard interfaces that are optimal for attaching persistent memory. We have NVDIMMs, NVDIMM-P, and CXL. And so with the second wave of persistent memory adoption, it's really now ready to begin. We can help meet the needs of these next generation systems with the memory performance and capacity that persistent memory provides. So this is a vision for future data center systems architecture that we can scale memory easily and efficiently and really meet those next generation system needs, enabling us to meet the data growth of the industry and still get value, unlock that value of data. All right, well, thank you very much. I appreciate the time. If I have some useful links and abbreviations here in case you need a little bit more reference here. And then you can go to the SNIA website here for our presentations. Thank you very much.